Ever look at medical literature and feel like you're staring at thousands of lines of legacy spaghetti code? Well, you are absolutely not alone, but here is the secret we are uncovering today. Clinical critical appraisal? It's really just a different flavor of data science and logic. Today, we're diving into an explainer of a fascinating curriculum called Evidence-Based Medicine for Techies. We are going to translate all that clinical evidence into the exact frameworks you already use every single day.
So here's our roadmap for today. We'll start with medicine from first principles, move into translating EBM into techie language, then appraising trials and tests, the skeptical techie stats, using the LLM research assistant, and finally, putting it all together. Let's jump in.
All right, section 1, medicine from first principles, starting with the patient, not a p-value. Because, evidence-based medicine shouldn't kick off with complex math. It really has to start with a real human being.
The entire foundation of this course is built on a first principles philosophy of guided discovery. It's inspired by something called Vibrounds, which basically means it prompts your analytical thinking instead of just spoon-feeding you the answers. It's Socratic learning at its finest. You aren't just blindly memorizing formulas. You're actually learning how a clinician thinks. You learn to evaluate patient history, the physical exam, SOAP notes, and even how to spot fake medical news, all before you even glance at a clinical study.
Think of clinical reasoning as a highly structured loop. You begin with the patient history, you formulate a highly specific question, you search for and appraise the evidence, and then you output a clinical decision. It is literally an algorithmic process. Once you start viewing it as a loop, all that medical mystery really starts to fade away.
Moving right along to Section 2, EBM in techie language. Honestly, this is my favorite part because it proves that clinical jargon is just a foreign language for concepts you already know inside and out.
For example, when doctors talk about formulating a PICO question for a patient, that's population, intervention, comparison, and outcome, they are really just talking about structuring a query. For a techie, this is exactly like building a search schema to query a database like PubMed. You're just defining your parameters to get the best data back.
It's amazing how instantly everything clicks when we do a direct jargon translation. Randomized controlled trials? Literally just A/B tests in the physical world. Likelihood ratios? That's simply a Bayesian update. And when clinical guidelines use the grade system to assess evidence quality, it's virtually identical to weighing test coverage against a ship decision in software development. Keep this mental cheat sheet handy. It completely demystifies the literature.
Okay, Section 3, Appraising Trials and Tests. This is where we learn to aggressively judge the validity of actual data by decoding the evidence pyramid.
Let me share one of the most counterintuitive insights from Lesson 3. A headline might scream that a new drug offers a 40% risk reduction. Sounds absolutely massive, right? But depending on the patient's baseline risk, you might actually have to treat 25 people, that's your number needed to treat, or NNT, just to help a single one of them. Understanding the difference between absolute risk reduction and relative risk reduction will completely change how you read medical news forever.
And this brings us to why you can't just A/B test everything. Lesson 6 dives into prognosis and harm studies. Sometimes you need entirely different study designs, like cohort or case control studies, to track long-term risks or rare side effects. You can't just run an RCT for 10 years to see if a chemical causes a rare cancer. It's practically and ethically impossible. You have to perfectly match your study design to your question type.
Then in Lesson 5, we get into diagnostic tests. When you're appraising these, you've got to look at specific metrics: sensitivity, specificity, positive and negative predictive values, and ROC curves. You're trying to figure out if the test is actually useful for your specific patient. It's not just a binary, is this test good or bad? It's a deep dive into its statistical performance characteristics.
But here's the kicker. Context is literally everything. The explainer highlights this mind-blowing fact. The exact same diagnostic test can be incredibly accurate in one population and virtually useless in another purely based on disease prevalence. A test's predictive value could swing widely from 8% all the way to 90%. If a disease is super rare in your patient's demographic, even a highly specific test is going to throw out massive amounts of false positives.
Section 4, the skeptical techies stats. Let's look way past those superficial numbers that usually trip everyone up.
Let's talk about what statistically significant really means versus the actionable range you get from a confidence interval. A p-value basically just tells you if a result is mathematically rare under the null hypothesis. But a confidence interval? That gives you the actual range of reality where the true effect likely lives. For real-world decision-making, it is infinitely more useful. Consider this explainer a threat hunting guide for bad stats.
You learn how to actively spot p-hacking, understand exactly why surrogate endpoints can be dangerously misleading, and critically read those limitations sections. We even get into funnel plots to spot publication bias. You know, that frustrating phenomenon where negative trials just mysteriously disappear into a drawer and never see the light of day.
But it's not all bad news. Counterintuitively, Lesson 4 shows how, via systematic reviews and meta-analyses, you can take weak, underpowered trials and pool them together to map out a highly confident conclusion. You learn to read a forest plot, measure the heterogeneity, which is the I-squared value, and appraise the review itself. It's essentially like combining several noisy sensors to get one crystal-clear signal.
Jumping into Section 5, the LLM Research Assistant, because let's face it, as techies, we shouldn't be doing rote formatting by hand.
The course includes this massive companion prompt library to help you execute every single stage of the workflow using AI to do the heavy lifting. We're talking using an LLM to formulate PICO questions, build complex PubMed search strings, rapidly screen abstracts, calculate your absolute risk reduction, and even stress test your own critical appraisal logic.
But, and this is a massive but, there is a non-negotiable golden rule here. The AI is an assistant, absolutely not an oracle. You must verify every single output. The LLM drafts, but you verify every number and citation against the original source. It drastically accelerates your workflow, but it doesn't replace your critical thinking.
So you've got all these statistical tools, the jargon translation, the LLM prompts, but we have to ask the ultimate question. How does a massive clinical guideline, built on the averages of thousands of trial participants, actually reconcile with the unique individual patient sitting right in front of a doctor?
Which brings us to our final section, Section 6, putting it all together with a full patient case. Time to bring all this math back to humanity.
Lesson 9 ties the whole shebang together. It maps the journey of one real, de-identified patient from the initial history through the PICO question, the search, the appraisal, right up to the final clinical choice. It beautifully bridges the gap between the sterile, perfect world of randomized controlled trials and the messy, nuanced reality of actual clinical practice, where a patient almost never perfectly fits the average profile of a study.
Armed with these first principles, you're ready to translate clinical evidence into the language you already speak. You know exactly how to spot the difference between statistical noise and true clinical significance. So, I'll leave you with this. The next time a massive medical claim crosses your feed, will you treat it as unquestionable magic, or will you break it down as just another dataset to debug? The tools are now in your hands.